So here in lecture 6.5, we're going to complete our exploration of multi-level logic. What we know from the previous lecture is that all of the action, all of the interesting factoring possibilities happen in the kernels and the co-kernels of Boolean equations expressed in the algebraic model. What we don't know yet is how do you actually find kernels of Boolean equations expressed in this model? Well, the answer is you kernel them. And so there's a lovely recursive algorithm to extract the kernels of a Boolean equation in this model. So let's complete our study of multi-level logic by figuring out how to go find the kernels.
So kernels are very, very useful, but now we have to figure out how to find them. So how do you find them? It's another recursive algorithm. You should not be surprised. As I've said multiple times in the VLSI CAD business, it's often the case that recursion is one of the most powerful techniques we use to find these things. But there's another couple of properties that we need of kernels to be able to sort of put all the pieces on the table so that we can actually create a not very complicated algorithm. So here's the first thing I want to explore. Suppose I start with a function f and it has a kernel, k1, in the kernels of f. And so one of the things I know is that I can write the Boolean expression f in this manner. I can say f is cube 1 times k1, right, and k1 is the kernel plus some remainder. So now I can ask a new and interesting question. What's true about the kernels of k1? Because, k1 is just a perfectly nice Boolean expression. It's in the algebraic model. It's clearly something that I can apply a kernel operator to. It's got its own kernels. Do the kernels that live inside K1 have anything interesting to say about F, which is what I started with? I took F, I did a kerneling operation on it, I got K1. I now want to take the kerneling operation and do it on K1 itself. Now what happens? So this is a kind of an informal kind of a derivation. We know this. We know that F is cube 1 times K1 plus remainder 1 because K1 is a kernel. Now suppose K2 is a kernel inside K1. Then I now know that I can write K1 as a cube times K2, which is a kernel, plus remainder 2. Okay. Why don't I substitute that expression back into the original equation, the one I started with, and then just kind of expand it all out? Well, if I do that, then I'm going to find that F is cube 1 times cube 2 times K2 plus remainder 2 plus remainder 1. Okay. Now let's just do a little bit of very simple Boolean algebra here. And let's remember that, cube 1 ANDed with cube 2, that's just a single cube. Q1 is something like ABC, and cube 2 is something like XYZ, and ABC, XYZ, that's just still another cube. Right? So I can actually take those two cubes and sort of pull them out. And if I just do a little bit of algebra, I'm going to get that F is cube 1 and cube 2, ANDed with K2, the kernel of K1, plus a bunch of other junk. And so the important thing to be able to say is that F is equal to a cube ANDed with a cube-free quotient plus other stuff. And the cube that we're talking about is cube 1 and cube 2, and the cube-free quotient is K2. And so what have I just said? I've said that F is equal to a cube times K2 plus junk, which means if I take F and divide it by a cube, I get K2, and K2 is cube-free. K2 is also a kernel of F with a different co-kernel. That's a remarkable, beautiful, practical result. Okay? I took F, I did a kerneling operation, I got K1. I take K1, I do a kerneling operation, I get K2. What can I say about K2? It is also a kernel of a F. So kernels have a hierarchical structure. They live inside of each other in this sort of tree, right? And so the terminology is that a kernel K in F is a level 0 kernel if it contains no kernels inside of it except itself. What that means is that if you were to apply a kerneling operation to it, you wouldn't find anything new. just kind of get yourself back with a co-kernel of 1. And a level n kernel is level n if it contains at least one level n minus 1 kernel, and no other level n kernels except itself. So level 1 kernels can have level 0 kernels inside them. Level 2 kernels can have level 1 kernels and also level 0 kernels. Right? And you can start with F, and it turns out you can extract all of these kernels in this very simple hierarchical manner. So that turns out to be a really useful insight. Now, that was my first result. Here's my second result. Another result from Brayton and friends. Co-kernels of a Boolean expression in sum of products form correspond to intersections of two or more cubes in the constituent SOP form. So intersections here means specifically that we regard a cube as a set of literals, and we look at common subsets. Right, so this is not like ANDing for products. This is just simple common subexpression. So if I had a function here, ACE plus BCE plus DE plus G, if you intersect ACE and BCE, you just get CE. If you intersect ACE and BCE and DE, you just get E. And what that means is that that's a potential co-kernel. Right, so you want to know where the co-kernels come from? Intersect the cubes in the Boolean expression in algebraic form. You want to have some sense of how the kernels arrange themselves. There is a hierarchy of them inside the function. That turns out to give us everything we need for a surprisingly straightforward algorithm. So how do you use those two results? We're going to find the kernels recursively. Again, you should not be surprised. This is just such a big, important concept. And whenever we find one, we will call our find kernels algorithm on it to see if there's any lower level kernels inside. And we're going to use algebraic division to divide the function by potential co-kernels to drive the recursion. But we're going to be smart, and so we're just going to organize the computation to look only at the intersections of the cubes. And if there's at least two cubes, we'll look at the intersections of those cubes, and we'll use that intersected result as our potential co-kernel. And one technical point is that, we're supposed to start this with a cube-free function f to make things work out nice. If it's not cube-free, you should just go find the biggest common cube in the function and cross it out, and then start. So here's the algorithm. And just as previously, I'm going to walk through the pseudocode of this algorithm, but then I am also going to show you a little kind of diagrammatic form how the algorithm works, which I hope will clear things up. So find kernels is our algorithm, and it's recursive. So you start with a cube-free expression for f, and the first thing you say is, all right, look, I don't know anything, so the set k of kernels is empty. And then for every variable in x, I say, are there at least two cubes in f that have that variable? If so, then that's a potential co-kernel. And what we know is that the way you get a kernel is by dividing f by a co-kernel. And what Brayton just told us is that you want to find a co-kernel? Those are intersections of the cubes, so this is what I'm doing. But I'm doing this, driving this process one variable at a time. So if there's at least two cubes in f that have this variable, let big S be the cubes that have that variable in them. Let co be the cube that results from intersecting all those cubes. That's a potential co-kernel. Then what we're going to do is take f and algebraically divide it by co, and that's going to be a kernel, we think. And that'll be returned at the end. But what we're going to do is recursively take f, divide it by that co-kernel, take that new kernel and say, hey, let's go look and see if there's anything inside that. And when we're done sort of exploring down the kernel hierarchy, as we come back up from the recursion, the last thing that we'll do is actually return that kernel that we found. Stick it on the set and return it back up. So the algorithm may seem a little bit complicated, but it's actually pretty straightforward if you just sort of build this little tree-like representation to see how things work. So let's just do this. We have an example, f equals ACE plus BCE plus DE plus G. And we're basically going to divide f by each of its variables and use that to start the recursion. So think of this as we're looking for co-kernels that start with this one variable in them, and then by sort of, recursing down, we'll be able to find everything. So we take f, and the first thing we say is, all right, let's go look for all of the cubes that have an a in them. And the answer is there's only one cube with an a in it, and what we know from the theory that we've got right now is that if there's not at least two cubes, there's nothing worth doing. And so there's no work to do, and so we just stop there. What about cubes that have a b in them? Well, there's only one of those. What about cubes that have a c in them? There's two cubes that have a c in them. Those cubes are, in fact, ACE and BCE. So, since we know that co-kernels are intersections of cubes and we have at least two cubes, we have something we can intersect, and so we can see what's going on. If we intersect them, we get CE, and that is a co-kernel candidate. So we're going to divide F by our co-kernel candidate to get A plus B. Well, that turns out to be cube-free, and that's good. That's actually a kernel. And the way this is going to work is we're going to recurse further on that, right? We're going to call the function on this A plus B, and we're going to do the same thing. We're going to say, so are any A's in it, any B's, any C's, and we're going to do it. And we'll actually get A plus B on the way back from that recursion. Next, we go to the D variable. Are there more than one cube with D's in it? No? All right, well, then we can stop that. How about E? Are there any cubes with E's in them? Yes, actually, there are 3 cubes with E's in it. And if you look, they are ACE, BCE, and DE. If we intersect them, we get a co-kernel candidate E. F divided by the co-kernel candidate E is AC plus BC plus D. That's cube-free, so that's a kernel. And again, we'll recurse by doing the same thing. Call the function on itself on AC plus BD plus E and check every single variable and see what we can find. So then when that returns, we'll go back and we'll check the last variable, G. There's only one cube with a G, so there's no work. So this is what happens at the first layer of the recursive call. Let's go look on the next slide and see what happens when each of those boxes that suggests there's more recursion actually recurses. So what's happening at the next level of the hierarchy? Well, here we found A plus B is a good kernel, and then we recursed down further, and so we would actually call the recursion with A plus B on it, and we would discover there's no work to be done on any variable. And so what would happen is we'd return A plus B with a co-kernel CE, and that's how that branch would finish itself. On the other hand, over here, when we did AC plus BD, BC plus D, and we did the recursion, there was actually some work. When we looked at A, there's no work to be done. There's only one cube with an A, only one cube with a B, and similarly only one cube with a D, E, and a G, but there are a couple of cubes. There are 2 cubes with a C in them, AC and BC. We intersect them to get a co-kernel candidate, C. We take F and algebraically divide it by co. We get A plus B. Turns out we get A plus B again. Right? Again, we find this same kernel with a co-kernel CE. Only what's interesting is that when we found it previously, we found it by immediately finding the co-kernel CE. And this time we found it by first finding the co-kernel E and then second finding the co-kernel C. Okay, that's a little awkward, but it's not wrong. It gets the right answer. And so we'll recurse on A plus B. We'll discover there's no more work, and A plus B will come back saying, hey, no more kernels living inside of it. We're done with that path of the recursion, and we'll return everything up the tree. So we get AC plus BC plus D, and we get A plus B. So with this algorithm, you can find all the kernels and the co-kernels too. And you get the kernels by ANDing the divisor co-cubes up the recursion tree. There's one tiny problem. You're going to visit the same kernel multiple times. And the solution is just you have to remember which variables you've already tried as you go down the paths of the recursion tree. So the problem is the kernel you get for co-kernel ABC is the same kernel you get for kernel CBA. The kernel algorithm doesn't know this. It's going to find it multiple times. There's a little extra bookkeeping to solve this, but I'm just not going to worry about it. Now, this is a fabulous result because it turns out that the kernels and the co-kernels are exactly the right component pieces for doing what we see here on this diagram. If I want to extract a single cube divisor from multiple expressions, I'd like to know where to go look. If I'd like to extract a multiple cube divisor from multiple expressions, I'd like to know where to look. So if I have F and G as nodes in a Boolean network logic model, I would like to pull out divisors which are either a single cube or multiple cubes. So a single cube is like ABC, a multiple cube is like ABC plus DEF. And use those extracted divisors to simplify the internal structure of the F in the G node. And when we started this lecture, you had no idea about the Boolean network model, you had no idea about the algebraic model, you had no idea about algebraic division, you had no idea about factoring, you didn't know how to extract them, and now you know a remarkable amount. You know that it turns out that the only place to look for multiple cube divisors is in intersections of the kernels. And the good place to look for single cube divisors is in the co-kernels. And you know that kernels live in a hierarchy inside each Boolean expression. So you want to go find a single cube divisor? Go look at the co-kernels. You want to find a good multiple cube divisor? Go look at the kernels. And algorithmically, we know how to do that in a simple deterministic manner. There's only one thing you really don't know how to do yet, and that's how do you deal with something that's got like 1,000 Boolean network nodes in it? Well, all right, that's what we're actually going to go do in the next sequence of lectures. So, what's our overall summary for multi-level synthesis models? The Boolean network model, it's like a gate network, but each node's in the network is a sum of products form. It supports many operations to add, reduce, or simplify nodes in the network. The algebraic model and algebraic division are big new ideas. They simplify Boolean functions to behave like polynomials over real numbers. We can divide one Boolean function by another. F equals D times Q plus R. Kernels and co-kernels of a function F in the algebraic form. The kernel is a cube-free quotient obtained by dividing by a single cube, which is called the co-kernel. Intersections of the F and G kernels are all multiple cube common divisors. There is only one place to look for good divisors, and that's looking in the intersections of the kernels. That's an amazing, big, practical result of engineering consequence. We're going to talk about how to use that. The problem, the big thing you don't know, is that you don't know what are the best common divisors to get. You know that the algebraic model and the kerneling operation kind of tell you what the right pieces are, but you don't really know how to deal with something with like a large Boolean network model with lots of nodes, and that's what we're going to talk about next. I'll just say also as an aside, the algebraic model and algebraic division are not the only options in multi-level logic. There are some Boolean division models and algorithms, and there are also some things that are sort of more expressive than the algebraic model, but less expressive than a full, complete Boolean model. But these things are more complex. There's a really interesting and rich universe of models and methods here. There's a couple of good references to read about these things. The paper by Bob Brayton, Rick Rudell, and Alberto Sangiovanni Vincentelli and Albert Wang, MIS, a multiple level logic optimization system from 1987. That's a really good primary source for the sort of the early historical evolution of these things. And also Nani DiMichele's synthesis and optimization book from McGraw-Hill. That's another really good place to look.